So indeed, I will present this preprint with this title, from which you can kind of infer already what Scott said, that lower bounds tells you that it's some kind of relaxation method or bootstrap method. And the key ingredient that we use is renormalization. So this is a method to compress bootstrap problems. That's like a one-line way to describe it. And this being an online talk, and if you are like me, who has enough attention for 2 slides, and then I start to wander off to the internet, I will just give you the story of the talk in 1.5 slides. So we have this many-body problem. We want to find the ground-state energy of a local Hamiltonian many-body system. Locality here means just that the interaction terms act on a few particles. And this is, of course, this cannot be done exactly in the general case, because, well, the wave function psi lives in this exponentially large Hilbert space. This could be also infinite dimensional. Okay, and in the first part of the talk, I will describe how this locality property gives rise to well, it's a great simplification of this problem, and it actually makes us think or hope that we could obtain good approximations. And when one talks about approximation methods, 2 general families of methods exist. One is the variational ansatz approach, which is, I guess, very well known to all of you. And the relaxation paradigm or bootstrap methods, I kind of regard them as synonymous. Maybe that's not fully exact, but okay, bear with me. This is a different approximation method. I will describe both of them and the kinds of approximations that they give rise to. So the variational approach, of course, gives us upper bounds to a minimum, and the relaxation method can be used to obtain the complementary lower bounds. Now, when we look at the success of variational ansatz methods, we see that their advantage is that physical insight can be used to kind of construct the good ansatz for a given system, the one that will kind of capture the physics of the system well. And one particular principle or idea that stands out in this sense is the renormalization group. So I will make the case that this combination of the variational principle with the renormalization group kind of combine the best of both worlds, in the sense that we get rigorous approximations. Variational principle tells us that we will get upper bounds. And the renormalization group made this method, allowed for a really efficient method, variational method. For example, the density matrix renormalization group, but in general, tensor-networks methods are all based on renormalization. And on the side of lower bounds, of relaxation methods, we still lack such this powerful framework for organizing how to say. You can think of it that we have some limited budget of the computational budget of the parameters in our ansatz, for example, and we need it to distribute it in the right place, and this has to be done in accordance to some principle, and this principle is renormalization. And our method attempts to do exactly that for relaxation methods. So we combine relaxation method with the renormalization group, and this allows to compute lower bounds efficiently for 1D systems where we tested this method, but hopefully also beyond. So efficient here is is of course is not meant in a computational complexity rigorous way, because we know that in general these problems are hard. But it's a heuristic which works very well where we tested it. So we just see that it exhibits efficient scaling. Okay, that's what I'm going to talk about. If you have any questions or comments, I will try to stop and ask for those. But yeah, just feel free to interrupt and ask. It's not so many people, so it should be fine. Any things that I should clarify at this point?
This looks clear to me. I'm a little. You say existing methods scale as the exponential of I assume that's the number of sites.
Right.
So relaxation methods without the renormalization group for some systems, like for certain systems, if you have a very short correlation length or something,
yes.
At least in practice, the scaling is quite good. So I mean, it depends on what precision you want.
Yes.
I think. Do you know exactly what the scaling is? Do you have some somewhat rigorous estimate for how much time you have to get to a certain precision without renormalization?
Yes. So for the 1D case, which I'm going to present, this scaling just kind of pops out from the plot. You just see it. And yeah, so I do have a plot about that. I think it's a general property of, like, for many body critical systems. This is of course not rigorous bulletproof statement. It's just all the methods that I know that yeah, try to do some kind of bootstrapping of many body systems. When you give it a hard instance, it will scale. The complexity will scale exponentially with the accuracy. Okay, thanks. Yeah, that's indeed. And n here is indeed not specified yet. You can think of it as the number of particles. Indeed. Okay, so let me start from the variational methods, and this is the so-called corner of Hilbert space argument, which I think is very compelling. So if you think of local Hamiltonians, these are very simple objects compared to general Hamiltonians. A general all-to-all just operator on this huge Hilbert space will be specified by an exponential number of parameters. Whereas a local Hamiltonian, for example, a nearest neighbor Hamiltonian on a spin chain, it will have number of parameters you need to specify such an object is n times the size of each interaction term, which is just some constant. So it scales linearly with n. So it's a much smaller family of systems, right? The Hamiltonian specifies a system, and well, if you associate to each such Hamiltonian its ground state, then you think, okay, there's polynomially many states that I'm interested in actually. So if I could restrict my optimization to this so-called corner of Hilbert space where physical ground states live, and if I could perform this minimization on this very small corner of the entire huge Hilbert space, I would be able to basically solve my problem, maybe approximately, but very well. Okay, and this is indeed the philosophy behind tensor networks methods. The understanding of, like, how to characterize the states that live in this corner and their properties, and how to use them in practical algorithms has been like a huge success of this endeavor that lasted the last couple of decades. And today we have very powerful methods based on those states, tensor network states. And beyond, like, quantum information theory and entanglement theory in particular, that were very crucial to develop this understanding. One thing that you can already see from their graphical representation is that they're very related to renormalization procedures. So indeed, in this reference here, you can read about the connection between tensor networks and renormalization procedures, but I mean, for my purposes, it's enough just that you see those pictures. And my claim here is that the renormalization group has been a very successful way to, well, construct variational ansatz. And this, while gives us very powerful numerical tools, it still gives us only a one-sided estimate, right? A priori, you don't know if your ansatz captures the true ground state, or if you're just specifying some state that is close to it, and which have a higher energy. So, rigorously speaking, any variational method will give you an upper bound on the true ground state energy. And in some cases, you might trust this method blindly, but a priori, you don't know. It might be that you're stuck in a local minimum, for example. And we therefore need also the approximation from the other side, so a lower bound. Now, let me say a few words where this is needed beyond the kind of obvious setting of physics and chemistry, where we would like, you know, to pin down the energy within a rigorous confidence interval. It can also be useful to benchmark variational methods, for example, for where we don't have exactly solvable models. We could come up with a lower bound and use it to benchmark our method. But beyond this kind of pretty obvious application, there is another application for lower bounds, which is maybe less familiar. And this comes from quantum information and quantum foundations. And this is the entanglement witness picture, if you will. So we can use Hamiltonians to detect or certify some properties of states of interest, or even to falsify physical theories. So the idea is that you have some set S, for example, the set of separable states, and you're given a state sigma, which might be outside of the set. So it might be entangled, and you want to detect that it's entangled. So what you would do, one way to do it is you would compute the minimum energy of some Hamiltonian that is specifying an energy axis in this picture. And if you know the minimum energy of all the states S, then by measuring the energy of sigma, you will see it has a lower energy, right? Because the energy is decreasing in this direction. And that will certify that sigma is entangled. Now, for this purpose, of course, it's good to know the exact energy is 0, but a lower bound is also sufficient. What will not help you is an upper bound. So variational methods cannot help you at all. Here, they can only say, I found a representation of sigma within my ansatz. That is, I can certify that sigma is within the set, because I can write down a separable state which equals to sigma. But the other direction of this decision problem can only be achieved with lower bounds. Another area where, of course, approximation methods play a huge role is quantum complexity theory. And I'm just going to mention that some of the things that I'm talking about, I'm going to talk about later, are important for this field, where satisfiability problems have the quantum analog is local Hamiltonians. Okay, but I'm not going to elaborate on that. And maybe that's the place where our method is. I don't have a concrete application in mind, but for detecting entanglement, for example, which is a very relevant practical application. So if you have a big system like a quantum computer with many qubits, then you will never be able to do full state tomography. And the locality of the Hamiltonian, when you translate it into this detection picture, it means that you will be certifying entanglement from local measurements only, not global measurements. So that's where we kind of see maybe another practical application of this approach I'm going to tell you about. Okay, so this is just to motivate why we need lower bounds, and we cannot get away only with variational methods. Next, I will tell you how lower bounds are usually obtained. Okay, but again, if you have any questions or comments. Scott?
No, all good. Let's go.
Okay, fine, excellent. So, so how can we use locality to get lower bounds? This is what I mean. This is what I refer to as relaxation methods. We write down our problem in the usual way, and just by plugging in the locality that our Hamiltonian is a sum of local terms, and that each such term acts as the identity on the rest of the system where it's not acting, we see that we can write down this problem in terms of the reduced density matrices on the corresponding patches or subsets of particles. So rho I is the reduced density matrix on this patch where HI acts. But in order to obtain the exact ground state energy, we need to impose this constraint that says that all of these states on the different patches should be compatible with a global quantum state. Okay? And this condition is very hard to verify. If I give you a collection of states and ask you, are these just random positive matrices, or are they compatible with a global quantum state? This is a hard problem. It's called the quantum marginal problem. And it's in fact as hard as the local Hamiltonian problem. From the point of view of quantum complexity theory, they're in the same class. And you kind of expect it, right? Because all we did, it was like, we used kind of the conservation of difficulty law, right? We just moved here in the original formulation, the intractable object was psi, which lived in a huge Hilbert space. And here, each one of these terms is very simple. You can evaluate this very easily. If you want, like for nearest neighbor spins, these are two 4x4 matrices, and there's n of them. But this constraint is very intractable. Okay, so it looks like we haven't achieved anything.
Can I ask,
yes.
What about the other direction? So it's quite clear that, and I'm not going to be rigorous in the complexity theory sense here, but it is quite clear that given the ability to solve the quantum marginal problem, you can use that to do the minimization over of the Hamiltonian over states. But the other direction isn't clear to me. So if I have the ability, if I have some magic algorithm to do the minimization over states, how do I solve the quantum marginal problem?
Okay, so this is a great point. Let me just say one more line, and then the next slide answers this question.
Oh, okay.
So what this allows us, this reformulation, while it didn't give us a shortcut to solving the problem, it allows us a different way to get approximate solutions. If instead of this intractable constraint, we now specify a weaker constraint, that is one that allows more states, rho I, in the optimization, this means we have enlarged the range over which our variables can take values. Therefore, the minimum will be smaller or equal. That is, we will have obtained a lower bound. This is why this is called relaxation, because we erase some constraints from this condition. I still haven't said how, but by removing constraints, we arrive at a lower value than the true minimum. And just one final remark about that, you shouldn't be surprised it's lower than the ground state energy, because by definition, we are dealing with non-physical states. We removed the constraint that forces them to be physical, that is, to be compatible with a global quantum state. Therefore, the solutions that we get are not physical kind of by definition, but they are still mathematically a rigorous bound on the exact solution. Okay, so the picture that you should have in mind is the following, and this answers your question, Scott. We have this target set over which we want to optimize a linear function. An Hamiltonian is just a linear function over this convex set. And it lives inside a larger convex set where we don't require any constraints between the row i's. Okay, and if you think about what it means to specify a convex set, okay, if that's the quantum marginal problem. We want to find out what is this set. We want to characterize it in some way. So if I give you a convex set, you can specify it by specifying all the supporting hyperplanes, the kind of tangent hyperplanes, which touch it for every direction in this huge space. And if you think about how that is done, so each hyperplane is defined by some vector, which is tangent, which is perpendicular to it. Let's call it a Hamiltonian. It will also be a local Hamiltonian because all it evaluates are the reduced states. It's a linear function on the reduced states. And how much to shift it is exactly the ground state energy. So if you know all ground state energies of all local Hamiltonians, you have specified exactly this convex set, which I mean, just draw a convex set in 2 dimensions and draw all the tangents to it. There's infinitely many of them, but each one of them is defined by a vector and a scalar, which is the ground state energy. It's just a kind of geometric convex geometry picture.
And so you only needed the ground state energies of local Hamiltonians because we're looking at convex sets of local states?
Yes, we are. All of this is within the vector space, which is like, take all your, like, let's say you have n reduced density matrices, you just write them in a huge vector one after the other. Like just take the direct product, the direct sum over I of row I. That's like just a long vector with all your reduced density matrices. That's your vector space in which you live, and Hamiltonians are just take a direct sum of all the interaction terms hi, and that specifies a linear function on that vector space. So it's really just convex sets inside this vector space.
All right, thanks.
Okay. Yeah. So the problem here is even like you can even sharpen this conundrum. Like we have a very small object that we need to specify to determine the energy. It's like like I said, the reduced states. You can think of them as being a bunch of 4x4 matrices, or even one 4x4 matrix if it's a translation invariant system. But in this example of the XXZ chain, it's even worse, or kind of, you need to specify 2 numbers to determine the energy density, right? The expectation value of sigma x, and the expectation value of sigma z. By symmetry of this Hamiltonian, the expectation value of sigma y will be the same as sigma x. So you really need to find 2 numbers that give you the minimum energy, but they are of course not independent of each other. And in this really great paper, you can see this plot, which is if you want, it's the 2-dimensional cut in this sigma x, sigma z plane of those 2 sets. So the outer triangle here corresponds to S0. So this describes the expectation values of any quantum state, regardless of whether it's compatible with the translation invariant global state or not. And the diamond plus the blue curve is the shape that is allowed for those correlations in a translation invariant global quantum state. And with the red dots, it's the 2D square lattice case. Okay, doesn't matter. The point is, you're looking for two numbers, but they are constrained in a very non-trivial way by the fact that they are expectation values of a global state. So, I mean, the fact that I'm talking about reduced states is kind of just the object that contains all expectation values for a local Hamiltonian. But you really can think of it as looking only at the expectation values that appear in the Hamiltonian. That's also fine. Right. So how can you what can you do if you cannot optimize over the set of marginals because it's too complicated? What can you do? Okay, and that's this complete hierarchies picture. So what you would do is you say, I cannot optimize over the set of marginals to get the exact energy, and I can optimize over this set of all possible positive states, positive and normalized. Okay, but that usually gives you something very bad. So what you could do, and that's very kind of old idea, and it appears in many different problems, and right, nothing new so far. I'm just I want to present how existing relaxation methods work. You come up with a list of increasingly complex constraints that describe well, increasingly a sequence of nested sets. So each set of constraints will include the constraints on the previous level and define a smaller set. So we start from S0, we add some constraints. Those constraints describe a set which I call S1. If we add some more constraints, it describes S2, and so on until at Sn for n equals infinity, we might even recover the exact set. So in this case, then I will say that the hierarchy is complete. And if we want an increasingly a better lower bound, we just need to solve for a more complicated set of constraints. So optimize over this set Sn for some increasing n. Okay, and usually it's not difficult to write down such a hierarchy. And I will give you an example in a minute. But that's where kind of the exponential scaling kills us. So usually we can write down these hierarchies, but we cannot perform the optimization for n higher than 2 in some levels or 10 in other cases. Like we cannot really take this limit of n going to infinity or even make n like large. So that's what our approach will try to overcome, and we managed to overcome this in the 1D case. But before I tell you about that, maybe you have questions? Scott, yes.
I don't think so. This is pretty clear.
Okay, so I made this slide where I kind of throw a bunch of references in, and it's not meant as a kind of a complete, of a complete survey of the literature. I just think it's useful to name some of the things that exhibit the same structure. And okay, just kind of for history. So Anderson bounds are exact. It's from 1951, and Anderson bounds are just optimization over S0. This gives you the realization that this gives you a lower bound. Well, here's the reference. It was used in 1951. Then, in quantum chemistry, what is known as reduced density matrix theory is also something that in this book by Mazziotti, you can read about like how it dates back to ideas in the 50s. Of course, the quantum marginal problem, as I mentioned, is very intertwined with this whole approach, and n-representability is just the quantum chemistry name for the quantum marginal problem. In quantum information, the NPA hierarchy is well, it's very similar to reduced density matrix theory, and it's also related to this Lasserre or SOS hierarchy for polynomial optimization. Not doesn't have anything to do with quantum, but a very similar thing happens there, where you have a hierarchy of semi-definite programs, and of course, bootstrap methods. I mean, I just threw a couple of references in. I'm not saying like that I know how to make use of this structure in each and every instance. It's the opposite, but I think that what I'm presenting here can potentially be applied to many of those things, and that's well, yeah, that's kind of my way of advertising what we're doing. Is like if you're doing some kind of bootstrap method where you have a hierarchy of constraints, I encourage you to think if you can apply something like what I'm going to tell you about there. Okay. Right. So let's see an example of this complete hierarchy and how we can overcome this exponential scaling in that case. So we were in the 1D translation-invariant setting. We have a spin chain, and we have one interaction term h, and this tau I just means it's translated to site I. So we have the same interaction term everywhere. And in that case, you can write down the ground state energy density, which I denote as ETI, as the following: minimization over space of the two-body reduced density matrix with the interaction term H, under the constraint that this two-body reduced density matrix is compatible with a global translation invariant state psi. So I write this condition like formally like that. Okay. Like I said, this is an intractable thing. We don't know how we don't know what to do with it. So what can we do? Well, we can reason as follows. And it's a very simple idea. If psi exists, then we can think of its reduced states of size n and n minus 1 and all the way down to 2. And those states will satisfy some compatibility conditions between themselves. So if rho n and rho n minus 1 are both reduced states of psi, then I should be able to obtain rho n minus 1 from rho n by partial tracing one of the spins. In fact, because of translation invariance, I can do it in two ways: by tracing out the spin on the left and tracing out the spin on the right. I should still get the same reduced state because of translation invariance of psi. So I define this arrow now to mean exactly this constraint holds between those two objects. And you can draw it like that. So each leg is like one spin, and it's a density matrix. So it has like ket legs and bra legs. And then this line that is connecting the two legs is just denoting the partial trace. So this is just some kind of graphical notation for exactly this equation. Okay, so far I haven't done anything because there's still this psi, this infinite dimensional object appearing in my problem, but now I can relax the problem by saying, let's forget about this part of the constraint and just optimize over rho m that satisfy these constraints. And this is indeed, first of all, it's a relaxation. Second, if you take a higher n, you strictly improve the energy that you will get. You will get a higher lower bound. And it's not difficult to see that for n going to infinity, you will indeed converge to the true Brownian energy. So in this sense, it's a complete hierarchy. But what is this now? This is a minimization problem of a linear function on row 2 with some linear constraints between the other variables, right? So each one of these is a positive semi-definite matrix. There's n of them. and minus one of them, whatever, and they satisfy some linear conditions. So this is an SDP, which we can just input into the computer and solve. The problem, as you can see, is that rho n is an n-body density operator. It's exponentially costly to do it in n. Okay, so in practice, we can solve this problem up to n equals 12 or 13. Okay. Okay, and now, and from this, like now, it's what we came up with. Everything that I told you so far has been like I said, it's like as old as I don't know. This is very old idea. Now I will tell you kind of the thing that we do. Okay, and for this, let us take these two constraints, the constraint between row 3 and row 4. Like I said, it consists of these two equations. And the constraint between row 4 and row 5, it consists of these two equations, right? Where this, again, it's just the partial trace from the left and the partial trace from the right give me the same variable, the same state, row 4. And this row 4, when I trace it, it gives me row 3, but in two different ways. Okay, and we can take one of these equations, and we see that if we apply a coarse graining map to both sides of the equation, it achieves two things. One, it's a relaxation. How to see it's a relaxation? You can imagine W2 being the zero map. So it completely erases this constraint, right? If I erase the constraint, there is no more constraint. I've relaxed the problem. More kind of exactly, this map W2 has a kernel. We want to map from two spins to one spin, so we want to reduce the dimension. If we reduce the dimension, there will be it will have a non-trivial null space. So some elements on which it acts, it will map to 0. This means that if I impose these constraints on the right, they are weaker from they're weaker than the constraints on the left, because I can add or subtract anything that lives in the null space of W to these equations. Is this point clear, Scott?
No, hang on, I'm thinking. So okay, what I think I don't understand is when you're actually implementing this in an algorithm, what is the information you're keeping track of, and what does coarse graining look like when acting on that information? I think that's what I've lost.
Okay, so let's say you are minimizing the energy of some Hamiltonian that is acting on row 3, but you don't want to allow all possible states row 3. You will constrain them by saying they should be obtained from row 4. And this row 4 should be a positive state. So you will have two optimization variables, row 3 and row 4. And row 4 is just there to impose some constraints on row 3. Yes. Because you can evaluate the energy from row 3.
Yes.
But now let's say row 4 is too big to fit in memory. Okay. So what I'm saying, you can take any map that is a coarse graining map in the sense that it reduces the dimension. It's also preserving positivity of states the way I chose to apply it. So WW dagger will still be a positive state. But that's like just mathematical detail. The point is the set of row 3s and row 4s that satisfies this equation is bigger than the one satisfying this equation. I allow for more states because give me a set that give me a pair, row 3 and row 4, that satisfy the left-hand side. It will of course still satisfy the right-hand side because I just acted, but I can still add something from the kernel of W, because W maps it to 0. It will not change this constraint. This constraint will still hold, but I've changed my variables row 3 and row 4 by adding something to them, and this just means I have more freedom in choosing them.
Okay, so I pick any, it's any linear coarse graining map, right?
Yeah.
And so I'm just saying, so the coarse grained row 4 is now it's effectively a 3-body state, so I can keep track of it.
Exactly, that's the next step. Yeah, that kind of so far you haven't achieved anything because you're still kind of explicitly writing things down in terms of row 4, but by the same logic, you see there is some degrees of freedom in row 4 that are never expressed in this equation on the right-hand side because they're always killed by W. So therefore, like you said, we can replace what we call as the compression step. We replace like all of this guy by omega 4, which is now a 3-body state, and it lives kind of on the output space of this map. And now you have achieved some kind of, you managed to save some memory, because if this was a 4-body state, now it's a 3-body state. This is, of course, not a lot that you saved. Okay, but is this now clearer? Like,
yeah.
In the end, you will replace. So my claim is, when you replace this condition with this condition, still demanding that rho 3 is a positive state and it's normalized, and that omega 4 is a positive state, a positive semi-definite matrix of these dimensions, then this condition, this will be a relaxation of the problem, and well, but we have achieved to compress this. So it will now, if you couldn't fit rho 4 into memory in your computer, now omega 4 may be it may be a bit smaller, so now you can fit it in memory. Okay, of course it's like not a big difference, but now in the next step we will see how to do it throughout the n particle chain. Okay, so that's the next step, how to iterate this. So we want to do the same for the next pair of constraints, right? We had these 4 constraints, and now we want to do the same for rho 4 and rho 5. This means we would like to apply a 3-body coarse grainer. Why? Because we want to prevent our variables from growing exponentially. So we want to, larger states, we want to compress them more. We want to coarse grain them more. Okay, so we would like to do the same thing, apply some W3, and then kind of rewrite the thing that was on the right-hand side in terms of omega 5, like we did like we did in the step before, right? We took this and we replaced it by that. But then we run into a problem that on the left-hand side, we're not allowed to write things in terms of rho 4 anymore, because we already said we replace it with this variable. So there's a problem, and how can we overcome this problem? Well, you realize that if you choose coarse graining maps that have the following structure, that W3 is obtained by coarse graining 2 spins and then adding 1 more, well, from the left or from the right, but that's kind of not the important part. This is the part that comes from translation invariance. The point is, we need an iterative coarse graining scheme. In other words, we need a renormalization procedure. We need to be able to take the 2-body coarse grainer and add 1 more spin with another coarse graining step, which I call R or L, depending on the left or from right. If we have that, okay, if this is like now a condition that I have to impose on the maps that I use, then we can plug it in instead of W3 on the left-hand side, and we identify again this guy, like rho 4 under the action of W2, that we can substitute for omega 4. So now we can substitute this with omega 4 and this with omega 5, and it will still be a relaxation. Okay, that's I mean, it's like getting into the details. I don't know how much we can also just like that was it basically. Like you arrive from this equation to this equation, which connects now the coarse-grained version of the 5-body state with the coarse-grained version of the 4-body state, but they are related, but by one more coarse-graining step, which is this RL map. Which what it does, again, it takes the output of the coarse graining of 2 spins and adds 1 spin more and coarse grain it again. Okay, that's like the complicated bit. The point is, if you have this condition for all M, that the M plus 1 body coarse grainer is obtained from the M body coarse grainer by adding 1 more spin from the left or from the right, then you can do this throughout the entire chain simultaneously, okay? And compress the whole thing into a problem that scales linearly in N. You look puzzled, Scott, so do you want to ask?
I think you just answered it, but is there a reason not to? I would have thought if I want to do some renormalization group idea on an L spin chain, then on an N spin chain, I would have done like a block spin type thing, right? I'll pair them off sequentially, and I'll apply the exact same coarse graining map to every pair, and that gives me one set of constraints, I think. And then with the computational cost coming from N over 2. But I guess what you're going for is linear scaling in N. Yeah, exactly. I guess what you're going.
Indeed, you can use different coarse graining schemes.
Okay.
And we tried this one, which is adding 1 spin at a time. This is more like what DMRG does. This is kind of the power of matrix product states, which are so if you're familiar with the density matrix renormalization group algorithm, it can be seen as a variational algorithm within the matrix product states ansatz family. Indeed, you can try other coarse graining schemes, and they give rise to other relaxations. And I have the results for both of these methods, the one with the linear coarse graining and the one with the linear in the sense like 1 spin at a time, and the block spin picture as well. And we can compare them and discuss which one, okay, this one works better, that's why I'm talking about it. Okay, but okay, that was kind of the tricky bit to figure out that you need some conditions on your maps in order for this coarse graining and compression thing to be relaxation of the original problem. And now we are left with this condition on the maps, which we need to find a way to satisfy, right? Like I need this for all M, this to hold for all M. And actually there's a really easy solution. This is matrix product states. If I build my coarse graining map by contracting M copies of the same rank 3 tensor, then, well, if I want to make the M plus 1 coarse grainer, I can just add 1 more tensor on the left or 1 more tensor on the right, and it will be the same as the M plus 1. So not important, point is very simple ansatz for such maps, okay? And then we can just use it. We can just okay, let me recapitulate what we're doing. We took the infinite spin chain translation-invariant energy problem. We arrived at this hierarchy of relaxations, which scales exponentially. And that's how the nth level of this hierarchy looks like. It involves this chain of states with the conditions between them. Now we applied our procedure, which replaced this chain of constraints by the one that says that rho 3 is related to omega 4, and the constraints look like this. So this, on the left-hand side, if you want, this is before the compression. This is just kind of the coarse graining maps we applied. Each coarse grainer is built from this single tensor. But now when we do the compression, the states in our problem are related as follows, and the right-hand side here is what we input into the solver. So coarse graining omega 4, like coarse graining these two systems on the left should be the same as partial tracing omega 5, and from the right similarly. Okay, and the tensor, the coarse graining map, the tensor defining the coarse graining map appears in these equations as kind of a hyperparameter. We cannot optimize simultaneously for the states and the coarse graining maps because they are multiplied. It's no longer an SDP. If we want to kind of use the power of the semi-definite programming framework, but we can just either fix some coarse graining map or do some gradient descent of the solution, optimize the solution with respect to the maps in like an outer optimization loop. Okay, and in fact we see that there's kind of a natural candidate for which tensor to plug in here, and this is the ground state approximation for the same Hamiltonian. So you run, what we do in practice, we run a variational algorithm that spits out a ground state approximation, which is defined by one tensor because it's a translation-invariant system. And we plug that tensor into our relaxation machine, which is basically, we plug in these constraints into the solver and go up to level n so there will be n of these omega m's, and that's what we do. Right. Any questions about that? I will show you the results of doing what this gives in a moment. But
so in practice, you have a way to estimate the gradients, or
for SDPs, it's like a known thing that you get the gradient for free. Okay, that's a cool thing. And this was like, we didn't know this, and then Slava Lichkov from the conformal bootstrap fame, he pointed out to us, hey, you can actually compute the gradient for free. They have a paper about this. It's called like the navigator function. But I mean, this is not something they did. It's like a pretty well-known semi-definite programming thing. But the gradient of the objective function with respect to the parameters in the problem, you get it just from the solution of the, anyway. Right.
Is it from the solution of the dual problem?
You need both. You need primal and dual solutions. Okay. But if you're using like interior, if you're solving the primal dual problem, then you get it for free.
Then you have both. Okay, great. Thanks.
Yeah. So I mean, I just okay. So kind of the vision is that this is a general thing which you can implement in many settings. I don't have many implementations because we just kind of did the one thing and then tried to do maybe to start doing projects where we apply this to other problems, like in 2D lattices and for bounding gaps. We have some ideas for how to do this, but okay, this kind of fancy diagram just says you start out from your original hierarchy of constraints. So this would be like you take your bootstrap method and you say, okay, there is money. There's the level where I include the so and so many constraints, but I can go to the higher level where I include more constraints, and this will specify some positive matrices, and there will be conditions relating them. And then you kind of coarse grain them and do this substitution where we substitute like the coarse grained rho for the corresponding omega. And okay, and we wrote down like conditions that you need to verify for this to hold, for the conditions on the diagonal being a relaxation of the conditions on in the first line. And the condition is that you need like this commutativity of each one of those squares, but whatever, it's just like some kind of technical abstract stuff. But I do think it's kind of useful, again, like take whatever bootstrap thing you're doing and try to see if you can find maps that satisfy this commuting diagram condition, and then maybe you can compress it. Okay, that's my kind of hope that I can find more problems where this gives really good results. Like I said, we did like for 1D spin chains, we did implement a different coarse graining scheme, which is based on block spin coarse graining. And if you want, this picture is like this diagram flipped sideways, where you have the original hierarchy of conditions, where the 4 body state is obtained from the 8 body state in 3 different ways, and the 8 body state is obtained from the 16 body state in 3 different ways. And then when you kind of block the spins on both of them, you can write down relations between the blocked things, and then you can iterate that. Whatever. Let me show you the results. Okay, so we took a bunch of spin chain models, and some of them are spin half. We have spin 1 Heisenberg chain. We have all of these are nearest neighbors, but this J1, J2 means there's a nearest neighbor coupling and a next to nearest neighbors coupling, J1 and J2. And some of them are critical and 2 of them are gapped. So critical, the correlation length is infinite. And there's indeed a difference in the performance, but okay, let's just see the results. Okay, so let's look at the Heisenberg model. This is a spin 1/2 Heisenberg chain. The y-axis is the error of the lower bound. So the exact energy minus the lower bound. This is positive, and we plot it logarithmically. And n is the biggest state that we include in our chain of constraints. So this is the kind of the system size. All of the results are still rigorous lower bounds on the infinite system ground state energy. Okay, it's an infinite system rigorous lower bound, just because of all the steps that I did were a relaxation of the original problem. The original problem was the ground state energy density problem in the infinite chain, right? That was our starting point. This is the exact infinite system ground state energy density. And everything we did was relaxing that problem. Therefore, we are talking about rigorous lower bounds for the infinite system. I just repeated the whole thing because Scott looked unhappy with what I said. Okay, I'm plotting here in black the exact, like this complete exponentially scaling hierarchy. So the LTI hierarchy is the solid black line with circles. That's the thing that we can compute up to n equals 12 or 13. And this being a log-log scale, you can clearly see the linear scaling. And this decreases as 1 over n squared pretty much exactly. Here it's exactly. In the XXZ chains, you have this even odd effect, but they are very close to 1 over n squared. And now for different MPS, for different bond dimensions of the MPS, we do our method. So if I increase the bond dimension of the MPS, this means I increase the coarse graining, the output space of the coarse graining map, and it allows me to keep more constraints, if you will. And then we see by increasing the bond dimension, so capital D is the bond dimension of the MPS that we use for the coarse graining. When we increase the bond dimension, we get tighter and tighter bounds. We are still always above the LTI because we obtain this relaxation by relaxing the LTI problem. But you see, we extrapolate, so we kind of follow the extrapolation of this 1 over n squared scaling into n. Okay, so n equals 60, we will never be able to solve the LTI problem for n equals 60. And here you can pretty much, it's pretty convincing that, okay, maybe not 60, but like 50 is still kind of a straight line from here up to n equals 60. So we obtain energies for an effective n equals 50. And these are rigorous lower bounds. And what was that point? Yeah, that it's a critical system. Like you can see that in the gapped transverse field easing model, everything behaves much better. You just kind of obtain, very good precision, but this is a gapped. Sorry, sorry, I now confused you completely. This is the critical transverse field easing model, so it's still critical, but it's just very little entanglement in this model. This is kind of a much more entangled or highly correlated system. Yeah, here the correlation length, I guess. Okay, I actually can't tell you exactly, but the picture on the right is how it performs for the other models as well. I plotted
Before we go on, so the memory and time costs to perform a calculation at certain n and d, it's linear in n. Memory is like d squared times d cubed, or what is it?
It's d to the 4 times d to the 4, because we have like bra cat.
Yeah.
You have 2
right.
D indices and 2 capital D indices, but bra and cat for both. Yeah, so it's actually pretty bad in that sense. But okay, in the end, I will show you the memory scaling of the LTI and of our method. So like number of variables in the SDP, measure of complexity. I mean, I don't want to do time complexity because first of all, it's a long time. Second, not all solutions are obtained with the same solver or even type of solver, and there you cannot really you can't really compare time. So it's really yeah, the only measure we could reasonably use is the number of variables. And for each one of the models, you see I plot the LTI, like the exact exponentially scaling hierarchy, with the dotted lines, and our method with the solid lines. And you indeed see that with the exponentially scaling hierarchy, as you expect, you get a diminishing return in accuracy when you exponentially increase the complexity. So it's flattening out, right? And kind of there, you know, the sales pitch here is that our method, you can see it scaling. It's a more or less a straight line. It has all these weird curves because when, like you said, when you increase the bond dimension, the accuracy increases, but also the complexity increases. So we kind of take the best result for a given system, for a given computational budget, and therefore the line does weird things. But you can clearly see like a linear scaling, which means polynomial complexity in the inverse accuracy. That's kind of the result. I mean, this answers your question, I hope, about complexity.
Yeah.
Okay. There's also like I mean, these are exactly the results, like the plots from the paper. So if you really want to dig into the details, you can find them there. The blue results are from this tree or block spin method. You can kind of see they give you something, but they're not as good as the and it's hard to push them further for different reasons that I will not get into. But you do get something non-trivial from them. Like, again, the reference value is like how well you can do with the exact hierarchy, because that's kind of the typical, that's kind of the vanilla thing that you would be doing if you didn't think of how to compress your problem. And the last thing I mentioned, which is kind of, that's like the last thing I will say, I guess, in this bar on the right. So I told you that the way we do the relaxation is we take a variational MPS solution and we plug it into our machine. That variational state has a variational energy, which gives an upper bound with a certain accuracy. And that's what I plot on the right here. So the kind of, for every lower bound, there's the upper bound from the same MPS. So it's more the other way. You solve variationally for like to get the best MPS approximation with a given bond dimension. This gives you an upper bound, and then you do our thing and you get a lower bound, and you see that they kind of match in at least in the order of magnitude is the same, and this is pretty kind of puzzling and remarkable, and we don't have a full explanation of this. It's just kind of nice that you or at least like people think of tensor networks and MPS especially as like a variational as an ansatz, and then suddenly you can take this ansatz, use it in a completely different way, and get a lower bound, and the two things converge together, which is rather cool, I think. Yeah, I mean that I've shown you this kind of last plot. And that's my summary. What the method that I presented to you does, it obtains lower bounds by some coarse graining procedure. The bound you obtain is depending on the coarse graining procedure. So for a given Hamiltonian, if you put the wrong coarse graining maps, you will completely ruin the thing. But you can find good coarse graining maps that will give you good lower bounds for that specific Hamiltonian. So that's kind of the message here, that you choose the coarse graining depending on which Hamiltonian you're solving for. And in terms of this picture, it means we're kind of optimizing over this blue set, which gives us a good approximation around a certain point, which is like the ground state of a Hamiltonian. And by changing the coarse graining maps, we can kind of rotate this shape and get good approximations for different Hamiltonians by changing the coarse graining maps. And that's it. I thank you for being over time, and thanks a lot.
All right. Thank you, Ilya, for the excellent talk. Let's see. Let's wait a bit to see if there are any other questions. Roger.
Scott, do you have the slides?
No.
Can we ask
Sure.
A recording will be posted online if Ilya's all right with it.
I mean, everything
but
everything is also in the paper, like all the kind of all of these steps that were kind of in the derivation. I pretty
but
much
it's
took
easier.
them.
It's easier for me having
Sure.
heard this.
I can send them. Sure, I can send
to
them.
connect.
Sure.
Perfect. Thanks.
Thank you.
Good question. I asked all my questions during the talk, so
Yeah, no, thank you for that. It made it possible to.
I sort of okay. I have a broad question. I think I just have to go think about this. But never mind the sort of microscopic mechanics of working with things like MPS or PEPs, where as you go to higher dimensions, it gets much harder. If I have a 2 or 3 dimensional system and I think I know what a good coarse graining map is from some inspired guess or something like that. And I can write it down as a linear map on the space of reduced density matrices, which I think is what you've done. Do you see any obstacle to just going through with that? I mean, is there some extra requirement on the coarse graining map in order for this to work?
Well, the requirement is, if you kind of analyze what we used in this derivation. So here, the coarse graining map that we applied was acting on legs where which the partial trace was not touching. So in some sense, they were commuting operations. More specifically, there was a different coarse grain, so the partial tracing map, we call it like marginalization map. So the marginalization map, strictly speaking, that we used on rho 5 and on omega 5 is not the same one, because this one was like partial trace identity, and here it was partial trace identity, but the identity was of a different size. So this condition, you can kind of write it as a kind of intertwining relation, that if you coarse grain and then partial trace, should be the same as if you partial trace and coarse grain. Okay, you can reverse the order, but it involves different maps. And this condition you can satisfy in different ways. The 2 ways that I explicitly talked about was where they don't touch. And the other way was in this method, where you need to impose exactly this condition that they commute in some sense, and for this you need okay, it's another technical detail, trace preservation. So if the maps are trace preserving and completely positive, then tracing out after coarse graining is the same as first as tracing out. And that is the thing that complicates this method further, and partially reducing the performance. And okay, and we like I said, we're working on applying this in other settings, and that's kind of the crux of the whole thing, to find the coarse graining maps that satisfy the conditions. And I tried to kind of, well, say, right, there's a prescription that so the commutativity of this diagram, whatever, never mind if it looks too complicated, it's just the thing that I explained written as a diagram. So the commutativity of the squares in this diagram are the condition, are a sufficient condition for doing the thing that I described. That's
all right. Thanks.
I missed every detail of the talk. But you said something like, you change co-squaring method and you can now study the bounds on different Hamiltonians by rotating this like blah blah. Sorry, I missed everything, but can you say a bit more about it? Because that was a mistake like line for me.
Sure, no, thanks for your question. So, I cannot tell you, like, if you give me a Hamiltonian, I cannot tell you this is the best coarse-graining map. If you use that, you will get the best bounds for this Hamiltonian. Let me go back to this. But I can tell you which maps are very bad. Like if you, it's quite easy to see that if you act on this equation with something that has the kind of four-body ground state in its kernel, if it annihilates the ground state of the four-body Hamiltonian, then you're just not gonna get anything better than what you get if you don't include this constraint arising from row 4. So there is like this kind of very clear understanding of that some maps are good because they kind of erase important. Some maps are bad because they erase important conditions, important constraints, and some maps are good because they keep only the essential constraints for that Hamiltonian. Right, that's kind of what's going on here. You can think of each one of these coarse-graining map as erasing some part of the linear constraints between the variables, right? Each one of these variables is like a huge vector, and you can write this equation down in a kind of in a basis or something where it's just a bunch of linearly independent constraints. And what the maps do, they erase some of the constraints because they map them to 0. It's like projecting the original constraint to some subspace, and some subspaces are good for some Hamiltonians and bad for others, and the other way around. I hope that clarifies it a bit.
Yeah, thank you.